Is water activity the most important pet food specification? Pet food production is one of the fastest growing industries worldwide, valued at $91 billion in 2018. Gone are the days of feeding your pet scraps from the table. Pet food today is carefully formulated to provide healthy diets, avoid allergies, and provide variety. With the increasing value of pet food comes increased expectations for safety, quality, and consistency. Correspondent with increased expectations has been more intensive governmental oversight and regulations. When the Food Safety Modernization Act was signed back in 2011, it included recommendations to make regulations on pet food production equivalent with human food production. The last of these updates and regulations went into place for very small businesses as of September 2018. The foundation of the FSMA approach to food safety is the utilization of hazard analysis and risk-based preventative controls, also known as HARPSI programs. The hazards associated with pet food are primarily focused on microbial spoilage by foodborne pathogens. Controls used to prevent microbial spoilage are lethality treatments to kill pathogens and product formulation to prevent microbial growth during storage. These controls must then be monitored through testing such as internal temperature during lethality treatment or water activity of finished product. While meeting the food safety regulations implemented in the pet food industry by FSMA are certainly critical to the success of pet food manufacturers, there are ways that a product can fail even though it meets all FSMA requirements. This is typically due to quality factors that render the product unacceptable rather than safety concerns. Examples would include chemical changes such as rancidity or physical changes such as texture and appearance. Water activity, along with temperature, is the most important determining factor for the rate of quality loss, and shelf life can be maximized by identifying the ideal water activity range for a pet food product. Water activity is defined as the energy status of water in a system and is rooted in the fundamental laws of thermodynamics through Gibbs free energy equation. It is measured as the partial vapor pressure of water in a headspace that is at equilibrium with the sample, divided by the saturated vapor pressure of water at the same temperature. The water activity covers a range of 0 for bone-dry conditions up to a water activity of 1 for pure water. Water activity is often referred to as the free water, and while useful when referring to energy, it is incorrect since free is not scientifically defined and it is interpreted differently depending on the context. As a result, the concept of free water can cause confusion between the physical binding of water, a quantitative measurement, and the chemical binding of water to lower energy, a qualitative measurement. Rather than a water activity of 0.50 indicating 50% free water, it more correctly indicates that the water in the product has 50% of the energy that pure water would have in the same situation. The lower the water activity then, the less the water in the system behaves like pure water. Water activity is measured by equilibrating the liquid phase water in the sample with the vapor phase water in the headspace of a closed chamber and measuring the equilibrium relative humidity in the headspace using a sensor. The relative humidity can be determined using a resistive electrolytic sensor, a chilled mirror sensor, or a capacitive hygroscopic polymer sensor. Instruments from Novasina, like the LabMaster Neo, utilize an electrolytic sensor to determine the equilibrium relative humidity inside a sealed chamber containing the sample. Changes in equilibrium relative humidity are tracked by changes in the electrical resistance of the electrolyte sensor. The advantage of this approach is that it is very stable and resistant to inaccurate readings due to contamination, a particular weakness of the chilled mirror sensor. The resistive electrolytic sensor can achieve the highest level of accuracy and precision with low maintenance and infrequent calibration. While water activity is an intensive property that provides the energy of water in a system, moisture content is an extensive property that determines the amount of moisture in a product. Water activity and moisture content, while related, are not the same measurement. Moisture content is typically determined through loss on drying as the difference in weight between a wet and dried sample. While useful as a measurement of purity and a standard of identity, moisture content does not correlate as well as water activity with microbial growth, chemical stability, or physical stability. Water activity and moisture content are related through the moisture sorption isotherm. The moisture content associated with a safe water activity will be different for each product and should never be relied on as an indicator of microbial safety. Each microorganism has an ideal water activity for growth. When a microorganism encounters an environment where the water activity is lower than their internal water activity, they experience osmotic stress and begin to lose water to the environment, since water moves from high water activity to low water activity. This loss of water reduces trigger pressure and retards normal metabolic activity. To continue reproducing, the organism must lower its internal water activity below that of the environment. It tries to achieve this by concentrating solutes internally. The ability to reduce its internal water activity using these strategies is unique to each organism. Consequently, each organism has a unique limiting water activity below which they cannot grow. Notice that an organism's ability to reproduce and grow does not depend on how much water is in its environment or moisture content, only on the energy of the water and whether it can access that water for growth. The table shown lists the water activity lower limits of growth of common spoilage organisms. These growth limits indicate that all pathogenic bacteria stop growing at water activities less than 0.86. while the growth of common spoilage yeast and mold stops at 0.70, which is known as the practical limit. Only xerophilic and osmophilic organisms can grow below 0.7 water activity, and all microbial growth stops at water activities less than 0.60. For a pet food product to be considered shelf-stable, its water activity must be less than 0.86 water activity to ensure that no pathogenic bacteria will be able to grow on the product as it sits on the shelf. Pet food with a water activity higher than 0.70 but less than 0.86 is considered shelf-stable but will still support the growth of mold and yeast. For pet food in the 0.4 to 0.7 water activity range, microbial safety may not be an important factor. Instead, chemical degradation can end the shelf life of pet food because reaction rates are at a maximum in this range. Chemical reactions such as Maillard browning, lipid oxidation, enzymatic reactions, and others can affect the taste, appearance, and nutritional value of pet food products. Water activity influences reaction rates by reducing activation energy, increasing mobility, and increasing the rate constant. Consequently, reaction rates are better correlated to water activity than moisture content. The reaction that is most likely to impact the quality of pet food is lipid oxidation or rancidity. This is a complex reaction with multiple possible pathways and requires the presence of lipids, oxygen, and free radicals to occur. Consequently, it is most often controlled through the removal of oxygen by nitrogen flush or the use of oxygen absorbers. Rancidity occurs when lipid oxidation results in the formation of odor compounds that result in a musty smell and taste. Dry pet food is often sprayed with a fat coating to maintain freshness and improve nutrition, making them particularly susceptible to rancidity. Pets will often reject food that has experienced rancidity, or the owner will discard food that smells rancid. Lipid oxidation is unique in that its rate not only increases as water activity increases, but it also increases at low water activity, making the general rule that lower water activity is better not true in all cases. To aid in determining the ideal water activity for slowing down chemical degradation, the reaction rate can be predicted using shelf life models. To be effective, these models need to account for the effect of water activity and temperature. The only fundamental shelf life model that includes both water activity and temperature is hygrothermal time. It is derived from a form of the Eyring equation where the constant values B, E0 over R, and R0 will be unique to each situation and are derived empirically through least squares iteration. Once the constants are known, any temperature and water activity can be used with the hygrothermal time model to determine rate of change at those conditions and hence the shelf life for a particular product as it relates to that change. For low water activity pet food such as dry kibbles, the most likely mode of failure is a change in product texture. Changes in water activity can affect both structure and texture, and each product has an ideal water activity range where the texture will be optimal. To maximize shelf life, a product must be maintained to its ideal water activity range and remain at that water activity during transport and storage. For dry kibbles, water activity is low and the expected texture is crisp and crunchy. But if the water activity increases outside of this ideal range, the kibbles will become soft and undesirable. On the other hand, semi-moist pet treats have higher water activity values and are expected to have a soft and pliable structure. If the water activity decreases outside the ideal range in semi-moist products, they will become hard and undesirable. Investigations have shown documented changes in crispness when equilibrating crisp products to various water activity values. The relationship between crispness and water activity was essentially linear, allowing the identification of a water activity range where crispness changed from acceptable to unacceptable. As the graph shows, crisp products will maintain their texture until they move beyond the critical water activity, where a sigmoidal loss in texture will occur. One way that water activity of dry pet food can change is due to moisture migration. In a package of pet food, water will move between pieces of pet food if water activity levels differ, regardless of the moisture content of the pieces. Water moves from high water activity to low water activity and not from high to low water concentration. If soft and hard pieces are combined at different water activities, moisture migration will occur and could result in textural changes for each of the components. To avoid this problem, the hard and soft pieces must be designed to be the same water activity. If components are combined at different water activity levels, a model can be used to predict the final equilibrium water activity. The other way that the water activity of dry pet food could change and result in undesirable changes in texture is due to exposure to high room humidity. As described in the theory section earlier, water activity is also the equilibrium relative humidity and related to storage humidity. If a product with a water activity of 0.4 is exposed to a storage relative humidity of 60%, the product will absorb water from the environment until its water activity is equilibrated to 0.60. This process, of course, takes time, but if not protected, the water activity of the product will increase outside the ideal range and become soft. Placing the product in moisture barrier packaging will slow down the change in water activity. The rate of water activity change inside a package of known moisture permeability can be modeled using Fickian diffusion, as can the required package permeability needed to achieve a desired shelf life. Once an ideal water activity specification has been identified, the next challenge will be to consistently produce product at that level. Ideally, a production setting such as oven temperature and belt speed could be established and remain the same through each production run, producing product with the same water activity each time. Unfortunately, there are outside factors that necessitate adjustments to production settings. One such factor is inconsistency in the incoming ingredients. An effective solution to avoid problems caused by inconsistent incoming ingredients would be to track the water activity of the ingredients and establish an acceptable range that will produce product meeting specifications with a limited amount of production adjustment. This could be easily accomplished by obtaining a subsample of incoming ingredients and conducting a water activity test. If the test does not meet the water activity requirement for the ingredient, it can be either rejected or the necessary adjustments to production can be made, knowing that typical settings are not going to work. Many pet food manufacturers measure the water activity of their end product, but the idea of using water activity to screen incoming ingredients may be a new but potentially useful concept. For pet food, setting an ideal water activity specification is a critical step in formulating for safety and quality. The specification can be set to avoid microbial proliferation, chemical reactions, physical and structural degradation, and moisture migration. Once the ideal water activity is determined, a combination of processing and formulation can be used to achieve that ideal water activity. The most common processing steps used to produce product that meets water activity specifications is to remove moisture through cooking or drying. However, pet food is typically sold on a weight basis, so removing water also reduces the weight of the product and results in lost revenue. Formulation can maximize the amount of moisture in pet food at the water activity specification through the addition of humectants that lower water activity, such as sugar, salt, and glycerin, without having to lower the moisture content. In addition, the careful monitoring of the water activity of a product on the production line will eliminate unnecessary energy waste and weight loss due to processing to lower than ideal water activities, which will maximize revenue. In summary, establishing an ideal water activity specification, formulating to meet that specification, and monitoring production with frequent water activity testing will ensure a safe, quality product with an optimal shelf life and maximum revenue. In short, water activity is the most important pet food specification.